Well, I would like all of you here at ESTIC to join me for the next few minutes as we travel through space and time to get a glimpse of how resources beyond Earth will help not only to further space exploration, but at the same time open the new space economy. So our trip begins here, in our planet, Earth, where we're facing an unprecedented level of interest and efforts, both internationally and also private and public sectors, also from science, technology, economics, finance, and law, to take advantage of the wide-ranging benefits that resources will bring to our humanity. So let's first travel back in time to join our ancestors, the Homo sapiens, a little bit more than 100,000 years ago, when they were facing droughts, environmental degradation, and population growth, and when they decided to leave their cradle in Africa, not because they were curious to see what was on the other side of the mountain or valley or for exploration. They left to northern parts of Africa, to Europe, and all sorts of parts in Asia because of basic survival. They were looking for water and food. But in the process, they learned how to develop technologies, how to control fire, how to preserve food, how to develop tools to live in harsher environments. Then, about 15,000 years ago, when they started crossing into the Americas, it was the first economic revolution, agriculture, a momentous occasion in humanity that allowed them to live first in small settlements, villages, cities, towns, and eventually entire civilizations. Then, in the 14th century, when the technology was developed to cross the oceans, then the search was for other elements, not basic survival, but that were important to society back then. For trade, for commerce, such gold, silver, spices, first on the east, but then they bump into this big continent that ended up having so many resources that they started cutting their dependence from their motherland. Then on the 19th century, it was about searching for oil all over the planet. This was the second economic revolution, oil that is still our main source of energy. And the search for resources continues to this day. In the last 20 years, it has moved from those very basic elements to the obscure parts of the periodic tables, where we find elements that are now part of your cell phones, the cars you drove here today, and they are fueling the renewable energy industry. Then, 60 years ago, we started exploring space. And why? Because of survival. Not because of basic needs, but it was the fight between the two superpowers, the Soviet Union and the United States, looking for technological superiority to gain the higher ground. Then we started launching probes to every planet and even beyond in the solar system to look for scientific answers of our solar system. But something happened on our way to heaven. We realized at some point that space had value, that could be useful to us. And that started with the very first communication satellite, Telstar 1, that established the first communication between Europe and the United States live. Now, the value of Telstar 1, it's not because it inspired the design of the soccer ball in 1970, because it started utilizing the very first resource in space, and that is the view from above, which is giving us weather forecasting, global communications, and global positioning system that can pinpoint every location of the Earth with extreme accuracy. And what it did is usher into the very first and now the only commercial use of space, a $250 billion industry based on telecommunications satellites. At the same time, it gave us a view of the fragility of Earth and the impact that we're causing in our planet on this relentless search for terrestrial resources, and open up our eyes to other options on how to conserve energy, how to probably recycle, but also to look other than Earth for resources in the future. And so the question arose, could there be any other resource in space other than the view from above? This is a pretty big space. There's plenty of real estate out there. And this is where it's important to define terminology. When I'm talking about a resource, we're talking about something that has value because of its utilization. If not, it's just an element of curiosity or scientific interest. And it is important to follow 3 steps if we're going to go after resources on Earth, space, or anywhere else. And these steps are the following. First, you have to have a recoverable resource. Know your element of interest with enough certainty technologically, economically, legal, environmentally, that you know that you can go after it. Second, you have to develop a technology to recover it. And as important as these two is to have a customer. And it's not sequential. These three are informing each other constantly so that we can devise or put together a program for development of space resources. These were the words that were uttered in the very first Space Resource Roundtable in 1999 by a pioneer of the space resources field, and they're still the guiding principles in the space resources community. So let's first take a look at the number one step, the recoverable resource, as we go into the solar system to look for them. So get ready, because now we're going into space. Now, the moment we enter low Earth orbit, we encounter a unique environment that is hard to replicate here on Earth, where we have microgravity and ultra-high vacuum and even swings of temperature and radiation. Conditions that we can use to create materials and products beyond Earth, so we don't have to carry it from Earth. That could be on the space station, in the future in commercial space station, or like it was announced just last week by a company, on these robotic factories where satellites will be built, and also spare parts and tools that we will need as we go into space. Then, as we keep traveling through space, we encounter the sunlight that can provide power to spacecraft, as it's doing right now. But in the future, that sunlight can be captured by dozens of solar concentrators that can beam that energy down to Earth with microwaves or lasers. And this will be with very ambitious infrastructure that can be built with resources from space. Now, I keep talking about using resources from space for materials and products and to create things like this. Where are those resources going to come from? Well, let's keep traveling. And now let's go to our nearest celestial body, our satellite near to Earth, our moon. The one that when we landed there 50 years ago, in terms of resources, it was quite a depressing view. In fact, the second man on the moon, Buzz Aldrin, when he stepped out of the lunar lander and looked at the lunar landscape, he described it as magnificent desolation. No air, no water, no wood, cows, plants, nothing that could be used for humans. Now, this view of our moon has changed radically in the last 60 years. As a result of several spacecraft and orbiters that we have been going around that have collected remote sensing data, it's the only place where humans have actually drilled and collected samples and even brought it back robotically with the Luna 24 mission from the Soviet Union. So all of these aspects is what we call exploration or prospecting. The very first step that one has to follow to identify the quality of the resources, the concentration and distribution. And we have gained much information about the moon in such a way that it has turned from magnificent desolation to a place rich in resources that we can utilize in the future. What are those resources? Well, let's take a look at them. First of all, even though it doesn't have an atmosphere, the moon has 45% of it is oxygen that is bound to the minerals that can serve as an oxidant or for breathing if you're going to have humans there. 21% is silicon, the most critical element in the semiconductor industry. Also, as a result of billions of years of the sun bombarding the surface of the moon, which is made out of this very fine dust called regolith, that is that way because it has been impacted by meteorites and asteroids for a long time. We have particles and ions from the sun that has been implanted on this regolith, such as hydrogen and helium. Even an isotope of helium, helium-3, that even though in small quantities is more abundant than on Earth. And some have suggested that it can be used in the future once fusion energy is under control and it can be used for industrial purposes. Also, every place where humans go, they're always looking for water. Such an essential, vital liquid. And not much hope was at the beginning in terms of water. The way that the moon is oriented towards the sun is completely illuminated, so there's no hope for any water molecule to survive in its surface. It has been found as part of what's called pyroclastic deposits or in minerals in very small amounts, parts per million, but nothing in large quantities. But from the very beginning of the space age, scientists started wondering, how about if there could be some places in the poles, deep craters where the light of the sun has never shone, and therefore those places could hold promise to have ice that's been trapped by impacts of comets and asteroids, and they're there in these very cold regions. So that search for that ice was initiated by the Clementine mission in 1994 with radar reflectivity, followed by the Prospector mission in 1999 that used neutron spectroscopy. And both of these missions, the data from those missions combined, gave us a glimpse that indeed water could be possible in these permanently shadowed regions. Confirmation of this came from the L-Cross mission in 2009 that consisted in 2 spacecraft. The first one going down to the surface, impacting it, and then sending a plume into space that detected about 5.6% of water, confirming that indeed there was water. One data point that must be followed, obviously, by more prospecting campaigns, but at least giving us hope that there is this very important resource in the poles of the moon. So now we can add water to the mix. What else is on the moon? Well, there's plenty of metals that we use every day: iron, magnesium, titanium. There's even gold in parts per thousands that came out on that plume of the L-Cross mission. Some regions of the moon have their rare earth, those elements that are so important to our society now. So these are just a summary of those resources that can be utilized on the moon, or also as materials to produce what I mentioned before on space stations and to construct things in space. But let's keep going forward. And let's catch up with these amorphous rocks that are floating around in the solar system, the asteroids, that usually are depicted very simplistically as this asteroid belt, as this belt between Mars and Jupiter. But due to perturbation and impacts, they happen to be everywhere, from small pebbles to rocks all across the solar system. And some of them are trapped in orbits very similar to the one that the Earth has around the Sun. These are the so-called near-Earth objects that make it easier for us to access them and obtain their resources. Now, from the point of view of space resources, even though they have a very complex classification, we can put them into 3 simple ones, based on what we observe here from Earth, what's called spectral types. The type C, which are the carbonaceous types that contain water up to 15 to 20%. The type S, or stony ones, that now start including elements such as nickel and iron and the precious platinum groups, platinum, iridium, rhodium, and things like that. Then we have the metallic ones. These are objects that differentiated, that collapse all the heavy metal in the center. Then they were destroyed by other impacts, and all that's left is the core, the metallic core of these asteroids, that contain extremely precious elements such as metals and platinum. So important are these elements that one the size of Aztec has enough platinum that has ever been mined on Earth and will ever be mined here. So that's why the interest that you may hear with asteroids. So now we add to the mix the platinum groups from the asteroids. But let's keep going. Let's keep going to what we consider the holy grail of resources, our red planet, Mars, that has also been explored by orbiters, several of them looking at the surface, also by rovers that are still roaming right now in the surface, one that even made it to the poles and looked at ice that was pretty much on the surface. And there are more coming in 2020, one from NASA, Mars 2020, and ESA's ExoMars 2020. So that year actually is going to be a very busy one in terms of exploration, as we will see. And what this objects were able to find in terms of prospecting is that water is abundant on the red planet. You can find it everywhere on the Martian regolith to 1 to 2%. If you want more, about 20%, then you have to go out the hydrated minerals between the 50 north and the 50 south bands, clays and gypsum. Even at the beginning of this year, there was a discovery from remote sensing that ice is present just a couple of meters below the surface around the 50-degree latitude, which promises resources for humans and also for production of propellants. The other interesting thing about Mars that none of the other objects have is that it has a thin atmosphere with carbon dioxide. And once you have carbon in the mix, you have fuels, you have hydrocarbons, and even plastics that you can develop in the surface of Mars. So these are the elements that one finds in the neighborhood of Earth. And I'm going to stop here because I can go into the moons of Jupiter and Saturn where there's subsurface oceans and even hydrocarbons raining down from Titan, but that's a little bit farther down the road. This is what I consider, and the space resources community considers, as reachable and extractable in the next 30 years or so. So we'll stay there. And this is just the natural resources. But when you go to space, you have to be extremely resourceful and look for anything that can be of use to us. And there are even parts out there that are man-made that can be used. And those are the hundreds of objects, debris, and trash that we have sent for 60 years or so that can be recycled and used for developing tools, spare parts, and even to making new satellites. So all of these things will have to be considered in the mix. So now the question arises. Which one of these space resources is more valuable? And I can even throw that question here, but I'm not going to do it because it all depends. It's a tricky question. Do you want it near term? Do you want it in the long term? Do you want those resources to bring them down to Earth or to utilize them in space? If you do a quick analysis based on the reserves that we have here on Earth and the economics of that, it shows you quickly that any metal or resource from Earth, bringing them down to Earth, doesn't make an economic sense. And remember, the resource has to make economic, legal, and financial sense. If not, it's not a resource. It will be all in the long term. Once getting resources from Earth becomes economically or environmentally not acceptable. So what makes sense is why not leaving those resources in space there so we can utilize them where they are without having to bring it from Earth. And this is important because think about this, for 60 years, every space, every element, every nut and bolt and human consumable and propellant that we have sent in the hundreds of spaceships has come from Earth. We depend 100% from our planet to explore space, and as we have learned from Earth, that's not a sustainable, that is not an efficient way to explore. It is also not an economical proposition. There's tons of fuel that are needed to overcome the gravity well of the Earth, and that results in a massive object that we have sent into space that are pretty inefficient. If you look at one rocket, this is the Saturn V, but any other rocket is the same thing. 90% of it is fuel that is needed to launch that tiny little 10% where your payload or the humans are contained. It costs $4,000 a kilogram to put anything into low Earth orbit, $35,000 to send them to the moon. And I'm not going to even go into Mars because then the dream of putting humans into Mars will remain just that, a dream. If you want to send everything to send humans and then bring them back to Earth. And so this is not a reasonable situation. We don't do things like this here on Earth. On Earth, if you go into these long cross-country trips, you don't bring all the fuel or all the food that you need in these trips. You use resources where you find them. You go to gas stations, you go to convenience stores, and the same thing has to be applied in space. Why not having fuel depots and getting your resources where you're going so that you can travel further and stay longer on planetary surfaces? So that brings us to that question, which space resource is more valuable? So you will soon realize that in the near term, it will be anything that can be of use to us to live off the land. And this is where terms that you're going to be bumping on are created. The in situ resource utilization, or ISRU, using resources in space. And other terms such as space mining, that means all the different activities that you need to develop or extract that resource, or space manufacturing. What is that you do with those resources in order to create new materials in space? So let's now take a look, now that we know what resources we have available, remember that second step, what technologies are needed to recover it. And so we'll follow the same step that we follow on Earth. On Earth, if you want to extract any resource, first you do what's called the prospecting. You find them, you know exactly the concentration, the composition, and where they are. Once you know that, and we already have talked a little bit about this, then you go into collecting it. If it's solar energy, it could be just a collector, but in general, if it's a material good, it will be excavation, it will be drilling, extraction. Extraction is actually the next step after collection. And finally, you utilize those resources, which is the utilization step. So we're going to follow those and to look at what technologies have been developed, what are the ones that are now being created, and the ones that we will need as we keep going to obtain resources in space. So let's start by the extraction or the excavation part. On Earth, we have been extremely successful on excavating material because we have three things. We have lots of power, we have lots of labor, and we also have hundreds of years that we're used to doing this under one gravity. We know what traction is. We know exactly how the material flows. But none of this will be present on the moon, Mars, and let alone the asteroids. Things are completely different. As you can see, not much labor, power will come from solar energy, and we have to adjust to different gravity levels. So we have to change our view from these big machines that we use to excavate here on Earth, big tires and moving a lot of equipment, to at the beginning look for more modest, more reduced type of excavators. Now, these excavators, even though they look small, they can be powered by electric, by batteries or by solar cells. They can be remotely operated. They can extract the very top soil, which is so rich with the resources that we need. Then they can start flowing. They're being designed so they can flow in different gravity levels, which are very different from what we have here on Earth. So several of this equipment has been already been developed, and they're still under development. Most of them, you will see they're continuously operating, continuously gathering the material, bucket wheels, bucket ladders. But sometimes you need even the backhoe types for berms and paths that will need to be constructed. All of them have to survive extreme temperatures and vacuum conditions. So they are a little bit different from what we have here on Earth. For Mars, the latest development just came from NASA Kennedy, the RACER machine that can extract or excavate the material that can be taken to the extraction plant and do that in a more efficient way. For Mars, also what you have to consider, since ice may be very close to the surface, is drilling systems. How you can drill through a 1 or 2 meter overburden, get to the ice, obtain that ice, and then collect it later. Which brings us to the extraction phase. How is that we're going to extract the precious resources? Well, on Earth, we have been very successful for many extraction systems, depending on the metal that you're looking for. Same thing will happen in space if you're looking for a certain type of metal, if it's water, if it's oxygen. Let's just look at one example of a technology that has been developed for about 10 years and is also under considerations in various places. And that is looking for oxygen on the lunar surface. This system is called the reduction system by using the ilmenite mineral, which is so abundant on the moon, and treating it with hydrogen that you can bring either from Earth or obtain it on the moon, because you only need a small amount because there's very little losses. You continually recycle the material at high temperatures, about 900 degrees Celsius. And with that, you obtain your water. You can split the water by electrolysis. And then you got your hydrogen, you put it back, but now you have your oxygen. The other advantage is that now you can start getting your metals, like iron. So you have to look at processes that will maximize the energy that you put into it to what you can get out of them. So in a typical prototype like this, and I'll show you one of those. You have your regolith coming in an auger. This is a prototype that was built years ago. Then you recycle it with hydrogen, you obtain the water, you electrolyze that water, get the oxygen, put it into a tank so that you can send it prior to humans getting there, if you're going to have humans on the loop, so that they can be ready. If you send a unit like this along with this excavator, you can have enough oxygen ready so that a human crew of about 5 can survive for 6 months. That's how far we have gone in terms of designing these systems. But they can be scaled up for a much larger needs. In fact, these systems have already been tested on what's called analogs, terrestrial analogs. These are places that look very much like you're in the moon. If you go to Mauna Kea and you land there, it's pretty much you have landed on the moon. And there, those systems have been tested for several weeks, not just the excavator and extraction machine, but other drilling systems and sintering plants for weeks at a time to see how they can be managed remotely and how efficient they are. And so far, they have been performing in a way that they have obtained enough oxygen for the amounts that I mentioned, for a crew of 5 for about 6 months. Again, this can be scaled up if we're thinking about more serious lunar outposts. The problem with these analogs is that the soil that you have is sometimes not close to what you find on the moon. The moon regolith is extremely abrasive, it's electrically charged, and it's quite different. So sometimes you have to put your equipment under other conditions by using so-called simulants for the moon and Mars. And even for simulants for one destination like the moon, you have to experiment with several. If you're looking for either mechanical properties, geotechnical properties, geochemical compositions, you have to test all of these systems under these conditions. So the search for the simulants has been going on for years, and now it's actually is been increasing so that we can put our system to the test before sending it to space. Other things can be extracted, not just necessarily from solids. On Mars, you have a CO2 environment. So the Mars 2020 mission will do the very first extraction of a resource in another planetary body by bringing carbon dioxide through a fuel cell in reverse. Now you apply power, and what you get is the precious oxygen that can be stored, again, if you at some point want to have humans that will be using it when they get there. Asteroids are a whole completely different world. Here we're dealing with a body that barely has any gravity or pretty much none whatsoever. And so we don't know much about them, so we need to do serious prospecting to know if they are solid, they are rubble piles, or what is that we're going to find. We also need we need to learn how is that we're going to attach to it. We learned from the Rosetta mission how difficult that is, and so we want to avoid having our spacecraft hitting it and then bouncing into space and being lost. So we may even be thinking about how to get a hold of this asteroid and bring it closer to Earth so that we can then have the time to extract it, because we have a very short time to access these near-Earth objects, so we don't have probably enough time, so we might as well bring them close to Earth. So all of these things have to be considered. And when it comes time to, and we can learn from the past, the Hayabusa mission in 2005 collected a few particles. The Hayabusa 2 just arrived about a week ago, and it's going to be looking at getting a sample. And the OSIRIS-REx will get there in a few more months. They're not specifically designed for collecting in an industrial scale, but at least we can learn from systems and from mechanisms of how is that we can collect the soil of asteroids without too much of with all the problems that we have attaching and docking to them. Which leads us to how is that we're going to extract elements from asteroids. Since it's so difficult to have any rover moving around or extracting, and if you start extracting something, it will just blow away. Why not using different techniques that we don't use here on Earth? How about collecting the power of the sun? And with a spacecraft redirecting that light, beaming it to the surface of the asteroid, heating it up until water and volatiles come spewing out of it, and then can be collected by a bag or a tarp, and then an ice trap it. So that's one process that has been now under consideration. It was explored by a combination of academic and private partnership, and it looked at smaller simulants and even meteorites that were exposed to high concentrated radiation. This is a case of a simulant of the Orgal meteorite. It's a type C. So what you will see here is how is that we're heating up this simulant with a xenon lamp that represents, it's trying to replicate the sun, how it heats up the surface and what happens afterward. So we turn on the light, and what happens, you start having thermal cracking, the water starts evaporating, that brings up not just the water, but materials starts coming out by a process called spalling, and that's the way you start drilling and mining into it. That's why we call it an optical mining technique, because not only you're extracting the material, but you're also drilling without having to touch the asteroid. So these are things that will be developed for those types of objects. Final step is utilization. How is that you're going to use those elements once you get there? Some of them are just simply use the lunar regolith. And a technique and the technology came a few years ago that revolutionized the way that we're going to do it. That's additive manufacturing or 3D printing. And already NASA and ESA are looking at ways to do not just small parts, but actually infrastructure that can be built on the moon by using this technology. Also, other utilization would be to collect the ice on the lunar poles, split it into hydrogen and oxygen, and that being stored and also fueling those lunar or fuel depots that will be collocated in strategic parts of the cislunar space. So that brings us to having covered what resources are out there, what technologies have been developed and are under development to extract them. And so we have to now touch on the third part, the customer. Who is going to invest on utilizing resources? And that's a very important question. One that will have to be solved here on Earth before we actually start sending massive infrastructure into space. So it is time now to come back from our trip, from where we were, as far as we went, to Mars, coming back through the near-Earth objects, going through the moon, going back to our planet where decisions like this will be made. So we can already see now that we're getting close to the European continent, to the Netherlands, and to the place where we started just a minute ago at the ESA ESTEC headquarters in beautiful Noordwijk. I hope I pronounced that correctly. And these are the places where ideas will have to come from on how government and industry will have to partner to make this possible. So let's take a look to see where we are at this point. Who has an interest on doing this? How much is this going to cost? And how are we going to make it possible so that everybody can benefit from the resources in space? So let's start right here at ESA, that is encouragingly sending a mission in the 2025 prospect that is going to look at volatiles on the moon, try to find out what those resources, and at the same time send a technology demonstration to look at those ISRU technologies, covering those two important parts, the prospecting aspect and also the technology development. And that's what's going on in Europe. In the United States, interest is coming all the way from the top. The vice president announced on the Space Symposium that we're going back to the moon, not just for technology development, but to harvest resources, even including another agency from the government, the Department of Commerce, that is looking at how is that going to partner between industry and government to make this possible. NASA, even though it has canceled its resource prospector, is looking at a different type of mission that will collect similar data, and more probably along with the commercial space sector. It's also putting funding into different mechanisms to develop ISRU technologies, prospecting technologies that will get us closer to making this a reality. And there's even a third government agency that is getting involved, and that is the United States Geological Survey, that is trying to bring its expertise on assessing terrestrial resources and how to do that in space. And it's not just the United States and the European Space Agency. It's other players in the world. India just announced that at the end of this year, it will send an orbiter and a lander to the moon. And guess what? They're going to be looking on resources from the moon. South Korea is sending in 2025 its first orbiter looking at ice on the poles as one of these objectives. Japan just put $1 billion, not on a specific mission, but on startups, most of them that will be looking at resources from the moon as they move aggressively towards this object. Luxembourg continues unabated its efforts to bring the commercial groups into its Space Resources Initiative to get more interest on funding this type of operations. The United Arab Emirates signed up a memorandum of understanding just last year with Luxembourg to look at their more ambitious plans on putting a colony on Mars about 100 years from now. But they're already looking into this. And just a couple of weeks ago, China and Russia announced plans, again, to go to space and to the moon, and specifically mention resources on the moon. So the interest is coming internationally, and it's building up towards making space resources a reality. But it's not just the governments. It's also the private industry. Starting with United Launch Alliance, that 2 years ago became the very first customer behind Space Resources, committing the design and development of its new upper stage, the ACES, that will be fueled exclusively with hydrogen and oxygen, no helium for pressurization, no hydrazine, hydrogen and oxygen that can be obtained and transferred in space. So they don't have to send it from Earth, so they can keep it flying indefinitely for their business case. For them, it's just sending satellites from low Earth orbit to geosynchronous orbit. Why bring in the fuel from Earth if you can do it in space? And so their idea is that water, and they don't care where it comes from, but it can come from the lunar poles, water that can be split into hydrogen and oxygen, and that can also be sent to low Earth orbit and a fuel depot, to L1, and then creating an infrastructure in which you will have fuel depots that can be utilized to refuel rockets. That can serve not just United Launch Alliance, but any rocket company that wants to use this and really making use of the cislunar space. They even put a price point in their different locations. For them, the business case closes at $3,000 a kilogram in low Earth orbit, $1,000 more than it cost them. They also will pay $500 a kilogram for the water on the moon. And so that has sent out companies and universities to look how to match their business case from the supply side. If we can create a mining infrastructure to get the water, produce the propellant so that we can then sell it to the United Launch Alliance. And so that set up a first study that we conducted along with ULA to look at different options. Where are we going to excavate? Are we going to drill? And even look into a third option that we call the thermal mining option. This is redirecting the sun from the peaks of eternal light in the lunar poles, bringing them down to the permanently shadowed craters so that you can then sublimate the ice and then collect it in rovers, ice cold trap that we move into the processing plant. In that way, minimizing any maintenance costs for big machines or extraction or drilling if that's necessary. So in that way, we looked at every little aspect. How much will it cost to develop this infrastructure? How much would it cost to launch it? How much would it cost to maintain it? And we put all those numbers together to see if we can match the ULA case. And interestingly enough, the results are quite encouraging. This is a nice mining business case for a 10-year production. What ULA said, we just need fuel and propellant for 10 years, for 3 launches a year, so we can move our satellites from low Earth orbit to geosynchronous. So we did that. So we matched the production rate, which is about 1,100 metric tons per year, and did it with a cost of development of $2.5 billion, which came a little bit lower than their 3.5. And the rate of return, it's 9%, which may seem low to some, but at least there's some rate of return that happens during those 10 years. But the situation becomes even more exciting when you bring the public sector. If now this facility can satisfy NASA needs, which is about 100 metric tons to launch a NASA vehicle to its gateway or wherever they want to go, then it costs just a little bit more for the development, but the rate of return is increased significantly to 16%. And producing savings for NASA, which are quite substantial, about $2.4 billion the first year, and then $3.5 after that. Why? Because they don't have to bring their fuel from Earth to have their ascent vehicle fueled. So that's the savings. And it will benefit everybody because it will reduce transportation costs to the moon by 3 times, making available for more countries and more people and companies that want to access space and the moon. And for Mars, it will lower it by a factor of 2 to 3, making that dream of putting humans in Mars possible. Because now you can have the fuel that you need to get there. Once you get to Mars, and you can produce it there and bring your astronauts back. So these are very encouraging results. But it's not just United Launch Alliance that is interested. It's also the other large aerospace companies that would like to make use of the propellant and also get into the business of development, the fuel depots, and even space resource utilization equipment. And it's not just established aerospace companies, it's new space, such as SpaceX, that announced plans to send humans to Mars, and even said possibly to the moon in 2024. Blue Origin, 2 weeks ago or so, discussed their plans to go to the moon, and again emphasizing lunar resources. And it is not just those companies that can access space with their rockets. It's all the small and medium and startups, companies that are, in the last 2 years, that have sprung out, positioning themselves strategically in all the links of the value chain of space resources that will be doing the identification, the extraction, the processing, the beneficiation, the refining, everything that will be needed to make space resources available. This is an exciting time in which companies, small to large, and governments are getting excited about doing extracting the resources from space. And it's all great. But there's one final answer to, a final question to answer that may be in your minds and in a lot of people's minds. Yes, it's great that we're going to go and extract all these resources, but is this legal? Can I just go and set up an operation and extract water from the moon, or take an asteroid, bring it down to where the lunar orbit and extract the resources? Well, in terms of that, all that we have going for us is the Outer Space Treaty of 1967 and the Moon Treaty of 1979, that specifically says that no celestial body will be owned by a country or by anybody. But when you go into these documents and try to take a look to see if it's possible to extract the resource without owning or possessing the body, then the language in these documents become a little bit more fuzzy. It's hard to really understand what is going on. And that is why, parallel to efforts to prospect, to develop technologies, to get commercial activities, there are already efforts in the legal aspects of space resources. And that is taking place by countries that are taking decisions on their own, like the United States 2 years ago, in 2015 actually launched its Space Resources Act, and Luxembourg follows suit with the first nation in Luxembourg that allows its companies to go after extracting resources. Now, that has obviously worried some, and so there are efforts to make this an international effort. And that effort is starting right here in the Netherlands with the Hague Space Resources Group that is looking at its legal ways that one can go and extract resources and making it available to everybody, a legal framework that will include the world to make sure that everybody gets a piece of space resources. They launched their 19 building blocks that they're planning to elevate to an international organization that will make such decisions so that the whole world can get involved in extracting resources. So again, you have to have your technology, you have to know your resources, have your customer, and have legal assurance that you can do that. Which brings us back to where we started a few minutes ago, in our Earth, where we're going to be making these decisions, where we're facing a unique point in time in which we're going to be going after resources to help us travel further, to stay longer, to increase space exploration, and finally start including space into the global economy. We have learned much from utilizing and extracting resources on Earth for hundreds of years, many positive things and many negative ones. So it will be up to us to use the lessons from the past to start incorporating those so that we can start utilizing resources not just in an efficient way, but also in a responsible and sustainable manner. It will be up to us, humans, on this rock to make this promise a reality so that everyone can have a bite of space. Thank you.